Hi, so today we're going to talk about the gravitational force and Newton's law of gravitation. So I'm basically going to teach you to calculate the gravitational attractive force between two bodies, and then we're going to use the thing that we derived in order to find out the orbit that this body must describe and how fast it's going and all that stuff. And for this we will need all these equations of circular motion that we took a look at the other day. So let's get started. Now, Newton's law of gravitation has a very similar shape to Coulomb's law of electric force. And the reason for this is that actually Coulomb was inspired by this law in order to develop his. In fact, he kind of fudged the data so that he would get something just like Newton's law of gravitation, and later on it turned out that he was right. So the idea is that we have two masses and they're separated by a distance r, and we ask ourselves how much force this mass does to this little mass here. And then we can proceed just like in the case of Coulomb and say, okay, so let's say this is the force, and then the more mass that I have here, the more force is going to be, right? Because if I'm being attracted by the sun, I'm going to be more attracted than if I'm being attracted by the earth, for example. So the more big mass, the more force. And because this has to be symmetrical, because if I exchange these two bodies, the force should be the same, then of course the more little mass, the more force. So then I need the little mass here. And just like in Coulomb's case, we need to remember that this force probably spreads around a sphere. And because it spreads around a sphere, it has to decrease with r squared, not with r. Because the force per square meter, to put it some way, is decreasing because it's getting spread over the surface of a sphere, which is 4 pi r squared. So this has to be divided by r squared. Good. And now we need a constant to account for the fact that our units are not the same as nature's units. And in this case, here goes a g, which we call Newton's constant of universal gravitation, or simply just Newton's constant. So you have Newton's constant, the big mass, the small mass, and the r squared. In reality, this formula is more complex because this is a vector quantity and the direction matters, but I'm not going to go into it yet. Now, the only thing that we need to take a look at is the units of everything. So, well, of course, we know that the force is expressed in newtons, this is kilograms, and this is meters squared. So we want to know the units of the constant. All right, so I know that I need to get newtons, and this has to be equal to the units of the constant, which I don't know, times kilogram squared, because I have two masses, divided by meter squared. So again, I realize that in order to get newtons, I need first thing newtons, and then I need to divide by kilogram squared and multiply by meter squared so that everything cancels out. So the units of g have to be equal to newtons, meter squared over kilogram squared. Simply because this way, these two things cancel and I'm left with newtons, which is what I want to get in the force. Now, just like for the electric field, there's such a thing as the gravitational field strength. But in this case, it is special, and we'll see why. So remember that when we had an electric field, so we had a charge, right, and that created a field. And at this point, we had a certain force. And we defined the electric field strength as the force per unit of charge. So we just divided the force by the charge that we put in here, and then we got the force per unit of charge that a charge that we don't know would receive if it was here. Now, in this case, the paper of the role of the charge is played by the mass. So now we have a mass that's creating a gravitational field, which is actually attractive, not repulsive. And then we have this other mass here. Actually, I'm going to call this big M, and I'm going to call this little m. And this mass is being attracted. So how are we going to define the gravitational field strength? Well, the same thing. In this case, we're going to call it G for gravitational. And we say, well, that's going to be the force divided by the gravitational charge, which happens to be the mass. In this case, this little mass here. Just like here, we had the little charge here. So I'm going to divide this by the mass. Now, the beauty of this is that if I can put this in my equation, and I get G m over r squared divided by m, and then I get that, of course, this does not depend on the small mass because precisely it's the force per unit mass. And that's the expression for the gravitational field strength. But there's something special about this, which is that in this case, the units of the electric field strength were newtons divided by Coulomb. In this case, the unit of the gravitational field strength are newtons divided by kilogram. But newtons are kilograms times meter divided by second squared, as you remember. And when we divide this by kilograms, we can cross out the kilograms, and then we get meters per second squared, which are units of acceleration, which means that the gravitational field strength, which is really the force per kilogram that something receives, is actually also equal to the acceleration that something will suffer in that field, which is not the case for the electric charge. And the reason this happens is because the inertial mass, what makes us hard to accelerate, and the gravitational mass, which is the thing that gets us attracted to gravity, are the same thing, thus they cancel out. This does not happen with electricity. The charge for electricity is not the same as the inertial mass, and therefore we just get newtons per coulomb, and that's it. This may seem trivial to you, but actually this little insight is what led Einstein to come up with his theory of general relativity, simply realizing that the inertial mass, the mass that makes it hard to accelerate somebody, and the gravitational mass, which is the mass that is related to gravity, are one and the same thing. Alright, now imagine that we have two masses. So imagine that, for example, this is the Earth and this is the Moon. So the Earth has the bigger mass, the Moon has the smaller mass. Let's imagine that this one's still, though it's really not still, and what's really happening is that these two things are spinning around each other. But let's imagine that this one is still. And then we want to know the force that this one's going to receive. Now, if this one already has a speed v going this way, what's going to happen is that this force is pointing towards the center of the motion. And this is going to create a circular path, which means that a mass inside a gravitational field, because there's a force that's always pointing towards the center, remember, this acts as a centripetal force. So the force of gravity in this case is our centripetal force, and it makes things go in a circle, because it's always perpendicular to the speed and it's always pointing towards the center. Remember, centripetal means that it points towards the center. We can actually calculate the velocity of this particle if we know the force and the distance. Let's see how we can do this. And then after we calculate the velocity, we will use this to calculate the period of the orbit. And that's how we can predict how long it takes for example, a planet to orbit the Sun, or the Moon to orbit our Earth. So let's do it. So what I'm going to do is I'm going to take, first we know that there's a force between these two things, which is the force of gravitation, which is g m little m over r squared. But from circular motion, we know that this force has to be equal to the centripetal force. Now pause the video and tell me the formula for the centripetal force. Hopefully you did it, and you got that the formula is mv squared over r. And now all I need to do is rearrange. So the first thing that I realize is that this little m goes, which means that the speed of something in orbit only depends on this mass, not this one. And it makes sense, because this is like the acceleration of gravity, right? The acceleration that this is going to suffer, which is going to determine the motion, does only depend here because it depends on the field. Very good. So then what we need to do is isolate this v. So let's do that. Then we have that v squared is going to be equal to g m over r, simply because I put this r over here, multiplying, and it cancelled out with one of the r's. And therefore, I can deduce that the speed of a planet orbiting another planet, or orbiting a star, is going to be gm over r, where r is the distance between the two bodies. Done. Piece of cake. Now I can use this to calculate the period of the orbit. And in order to do this, I just need to use common sense, really. So now that I know the speed, I also know that if this is my big planet, this is my little planet, this length here is 2 pi r, right? So how long am I going to take to traverse this 2 pi r distance? Well, all I need to realize is that the time, so remember that v equals distance over time, so time equals distance over speed, right? So I just need to take this speed, take this distance, and insert them here. Alright, so let's do that. Let me zoom out a little bit so that this becomes a little easier to read and to write on. Okay, so we have that the period, because that's what we're looking for, has to be equal to the distance, which is 2 pi r, over the speed, which is square root of gm over r. And now what I'm going to do is I'm going to square the whole thing, simply because I don't like having square roots in here. Nobody likes square roots. So t squared equals 4 pi squared r squared over gm. And then this r here is actually dividing, which means that it's going to be go up multiplying. So instead of this squared, I'm going to have r cubed. And there you go. We have that t squared is proportional to r cubed. And this is a law that was discovered by Kepler way before Newton came up with his law of gravitation. And what Newton did was he was able to explain this law that Kepler had found by experiment, really, just by taking a look at orbits and finding some regularity. He was able to explain it simply by using his law of gravitation and deducing this equation, which was quite an achievement. What happens though if I have two bodies and I want to know the gravitational field at some point between them? Now, in this case, this guy is going to be pulling this way, and this guy is going to be pulling this way. So I'm not really sure what to expect for the force here in the middle. So the first thing that we need to do is, well, okay, so imagine that the distance here is d, this one's r, and then of course this one here is d minus r. And then we can ask ourselves what the total force, well, what the total gravitational field is here. Now, this is actually easier than it looks. All we do is add them up. But we need to take into account the directions, because the gravitational field is a vector, and as such, it has a direction. So this gravitational field of this guy in here is pointing towards this mass m. Okay, so let's call it G big M. Whereas the one from this guy is pointing towards this little mass. So there's this G little m. And the total G is going to be equal to Gm, imagine that, like taking this to be positive, minus G big M. Simply because they're pointing in different directions. If they were pointing in the same direction, so for example, if this guy was here, then they would both point the same way, and then they would be adding up. So it's very important that you remember that these things are vectors, and therefore they add up as vectors. Now, what happens if we have a situation like this? Instead of calculating the gravitational field here, we calculate it here. Now let me just, let's just remove all this. So I want to calculate the field here now. Well, it's actually a little trickier than before, because now this one points this way, and this one here points this way. So these guys do not just add up. These guys are vectors, and they add up as vectors, which means parallelogram rule. Yep, something like this, and then the total goes this way. How can we do this mathematically? Well, as we always do these things mathematically, by taking components, which means that you're going to be forced to consider this angle here, that this mixed with that. You're going to be forced to consider this other angle here, let's call it theta 2. You're going to be forced to take components of both, so component 1, component 2, and then you're going to have to add the components. Hence all the work that we were doing with vectors at the very beginning, where you had all these vectors and you had to add components, and then you had things like this. And they asked you, well, what's the total? Well, this is exactly what we need to do when there's several bodies acting on one point. We get exactly this, and then we have no choice but to take components and add up. Is this a pain? Yes, it is. But it can't be helped, and we need to learn to do it. So, good luck when you try it in class. Alright, so we've come to the end of the lesson. The theory is not very hard. What's hard is doing the problems. As you can see, we've described the relationship between gravitational force and centripetal force. We've applied Newton's law of gravitation to the motion of an object in circular orbit. Yes, we haven't done this because that's your job. And finally, we have determined the resultant gravitational field strength from two bodies. Of course, I haven't spoon-fed this to you because you need to know how to add vectors, but I'm sure that you'll be able to do this in class with a little bit of help. All right, guys, so I'll see you in class.